Hello everyone, welcome to our webcast, Applications of Time Domain Reflectometry. Today we'll be talking about the basic principles of TDR operation and common TDR applications for power cables. My name is Yerto, I'm the Marketing Communications Engineer for Mega North America, and I'll be acting as the moderator for today's presentation. If you have any technical issues or questions for our presenter during the session, I'll be supporting you. On the right side of the screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red. You may also notice that there are two audio options, telephone and mic and speakers. The mic and speakers options uses V over IP, so you may experience intermittent audio lag due to bandwidth. At any time during the presentation, you can switch over to the telephone audio option. You will receive a copy of the presentation afterwards, and remember, you can ask questions at any time during the presentation, and I will interject your questions as we have time. Our presenter today is Marshall Bird, Mega's Sales Manager for Cable Products. Marshall is based out of Colorado. Thank you for joining us, Marshall.
Thank you, Yer. So today we're going to talk about time domain reflectometers, TDRs. Before we get started, I would just say that I've worked with the cable products for quite a long time, but what I haven't done for a long time is webinars, so I'll be a little bit rough here, but I'll try to get the points across, and we'll try to have time to answer questions. TDRs, time domain reflectometers, there's a lot of different types of TDRs and different applications and methods. This webinar is going to focus on a specific type and application, basically using a TDR on a primary medium voltage cable, specifically cable fault location is what we're going to focus on. So we're talking about a TDR that would be connected to a cable like this, a medium voltage cable. There's a center conductor and some type of shield, some type of neutral concentric. These particular TDRs come in different flavors. There's three-phase, there's single-phase, there's standalone, there's integrated. If we look at the nomenclature for TDR, starting with T for time, the time is just how long did it take for the TDR's pulse to travel down the cable and back. Domain, unlike a radar or TDR out at an airport, whose domain is air, the domain of these particular TDRs is the pulses traveling down the cable's insulation. In essence, the pulse is trapped between the center conductor and the neutral. We'll get into it later, but these TDRs require two parallel metal conductors, and whatever is between those two parallel metal conductors is the domain. Reflectometer, some of the TDR's outgoing pulse will reflect back from impedance changes between the center conductor and the neutral. The ABCs of our particular type TDR, the TDR pulse board generates a high frequency, low voltage pulse. Typically these pulses are in the 20, 25, 30 volt range. This pulse then will travel down our medium voltage cable. As stated before, it's trapped between the center conductor and neutral concentric. Some of the pulse will reflect back from any substantial impedance change along the cable. And all the remaining pulse is going to reflect back from the far end. And with a pre-known propagation velocity setting, the TDR will display and calculate distances to these impedance changes. Okay, so what does all that mean? Here we have a TDR connected to a medium voltage cable. And, you know, it's not shown clearly, but this cable, the neutral concentrics are grounded at each end, and the TDR is actually connected to the neutral concentric and the center conductor. This particular medium voltage cable has a splice in it. So the TDR is going to release a low voltage pulse when we tell it to. The pulse is traveling down the cable and reflecting back. And in the middle of the screen, you can see this blue line. That's the trace or the impedance signature that we would actually see on the display of the TDR. And what we're interested in is we can see a reflection off the splice, and we can see a reflection off the far end of the cable. And also over here on the left-hand side, I didn't circle it, but this is a reflection off of the splice right here at the connection point. I would call this the characteristic hookup impedance. There's always a bit of bump up, bump down on the left-hand side of your display screen. Okay, here's a picture of a real trace, and you can see here there's a splice, a reflection off the far end. Over here on the left-hand side, it's kind of chopped out of the display picture. It's been slid off to the side, but a characteristic hookup impedance. And also in this, you can see where we've put a marker, a cursor, if you will, that shows the distance to this bump up. So the end of this cable was at 549 feet. Okay, one of the common things that's done with TDR is to verify that you are actually seeing all the way through to the end of the cable. It's pretty easy to verify this. You can simply go to the far end of the cable and ground the center conductor. So in the middle of the screen, the blue line shows the trace is seen on the screen. And if we look down at our cable here, we've gone to the far end, or we've sent the apprentice, if you will, to the far end. And right now, the far end is just parked or stood off. But if we have the apprentice take the center conductor and ground it, so the far end's been grounded, and you look at the trace in the blue line in the middle screen, you can see how the signature has changed now. With an ungrounded, we remove the ground, we get a bump up. When we apply the ground, we get a bump down. This verifies that both metal conductors are intact all the way to the end, and that the radar is indeed seen to the end of this cable. The TDR has some limitations. As I stated, you have to have two parallel conductors. Generally, this is the center conductor and neutral concentric. However, any two parallel metal conductors will work. A common example would we could connect the TDR phase to phase on say in a three-phase environment, and then the radar would see down to where either or both of those phases stopped. So this brings us, the TDR is blind past where either of the parallel conductor ends. And down below, we have a TDR connected to a cable, and in this case, the neutral concentric is corroded away at some point. It could just as easily be a broken center conductor at that location. When we apply the TDR pulse, instead of seeing to the end of the cable, the TDR, 100% of the signal reflects off of this broken conductor. So this is, you have an expectation to see a certain distance down the cable, and we don't see all the way down to the end. If we go back to the prior slide, this would be where we may go to the far end and put a ground on and off to verify whether we are truly seeing to the end of the cable. And in this case, where one of the conductors is broke, we would never see this end marker here bump up or down, because literally the radar is blind to the far end of the cable. Okay, so how do we identify this type of situation? Like I said before, we can verify by grounding the far end, and we can also take the TDR to the other end and shoot back the other way and compare the distances from each side of the cable. Let's talk about the three main TDR signatures. Now, there's more than just these three, but these are the three big ones, the important ones. Is we have this bump up, this profile over here. That's a reflection off of a high impedance. Typically, this would be a reflection off the stood off or far end, or where one of the broken, or we have a broken conductor of some type. Next, we have the opposite, a bump down. This is a reflection off of a low impedance. And I should pause here when I say high impedance or a low impedance. Basically, this impedance is determined by how far apart or how close the two metal conductors are. So if the conductors spread apart or stop, that would be high impedance. If the conductors get closer together or touch each other, that would be a low impedance. But moving on, so the bump down, that would typically be a reflection off of a ground that we applied somewhere on the cable, or metal-to-metal contact. In a faulted cable, that could be like a stop sign or a ground rod that's been driven right through the conductor and has bolted the two metal conductors into contact with each other. And then you also see we have this downward V shape represented in red. This is a special case where it's arc reflection mode, where we combine the radar with a thumper. We'll talk about this more later, but the thumper makes a temporary short at the fault, and the radar shows us this downward shape at the fault location. The third signature is what I call a wiggle. It's where the signal, the radar's pulse, has gone through, down to the far end, and reflected back. So the signal's actually going through this impedance change. Typically, these would be splices or transformers. They look exactly the same, except for the transformer signature will have a higher amplitude. It'll be physically bigger than a splice. Other than that, they pretty much look the same. Now, there's 4 common TDR adjustments if you're doing manual adjustments on a TDR. Number 1 is the propagation velocity. This is a setting. It's really not an adjustment. It's a setting that you set to ensure accurate measurements. What the propagation velocity is simply how fast the TDR pulse travels or propagates down any given cable. So a big diameter cable is going to have a lower propagation velocity, more impedance, if you will, than a small diameter cable. And you know, we've predetermined what these propagation velocities are. We'll talk about that more later. Another common adjustment is the display range. The displayed range is adjusted to fit the cable length onto the display. A lot of people confuse display range and cable length. The displayed range is simply how big the viewfinder is on the display. In other words, if we have a short cable, we don't need the viewfinder set really long. We can shorten it up. And on the opposite, if we have a really long cable, we have to widen up that viewfinder to make the cable, the long cable, fit onto this little 6 or 10 inch display. Number 3 is the gain. It's just the y-axis amplitude adjustment. That blue line, we can make the signatures increase or decrease by adjusting the gain. Typically, if you set it manually, you would adjust the end reflection to be somewhere between 50 and 75% of the maximum amplitude. And then finally, we have cursors or distance markers. These are markers that they're vertical lines that we can move left or right along the blue trace to mark distances to points of interest. Okay, let's move on to arc reflection, or distance to a fault. This is the most common method in the United States for prelocating distance to a fault on a medium voltage primary cable. And what we do here is we combine a high voltage thump with a low voltage TDR pulse. Now what the high voltage thump does is this high voltage pulse travels down the cable, and when it reaches the broken insulation, it arcs across at the fault. So right there at the fault, we've used high voltage to create an arc. And during the arc, there's current flow between the center conductor and neutral concentric. In essence, this high voltage pulse is creating a temporary short between the two conductors. It's just for a millisecond, but for just a little while, we have a short, an electrical short. Now, the low voltage pulse from the TDR is sent at the same time as triggered by the thump, so it knows when to go look for that short. And the TDR's low voltage pulse is going to travel down the cable, and hopefully what's going to happen, it's going to reflect off of that temporary electrical arc or short. In essence, the TDR sees this temporary short. So what this looks like is here we have a medium voltage cable, and you can see somewhere in this cable, this red lightning bolt represents broken insulation. There's a fault in this cable. Now when we just hook the radar up to it, in the low voltage mode, we see our characteristic hookup impedance on the left. We see this nice flat line, and right here where the fault is, we don't see anything because there's not enough impedance to reflect off of that fault. What we do see is the far end of the cable. Now with our thumper, we'll charge up a capacitor. We'll release a single shot, if you will. It's going to be, that energy is going to be released through a filter. That high voltage pulse is going to travel down and arc at the fault, and the radar signal is going to reflect back. And now what we see up above is we see a second trace laying right on top of the blue trace, and right at the fault location, the second trace now is reflected off of that short, and we have the downward V shape. If we back up and just go through that again, so the thumper does a high voltage shot. Whoops, the thumper does a high voltage shot, creates an arc that gives a target for the radar to reflect off of, and we can calculate a distance to that fault now. And down below here we have a picture of a real fault. We read the trace from left to right. You can see the red and the blue trace actually black in this picture. They're tracking together, and 178 feet, right at this location right here, the red trace dips down, and we have that profile of a short. Another way that I typically explain this is that's where the radar went to ground. It goes down at that location. And you can see we have two distances tagged with our cursors. We have the open, the stood off far end at 550 feet, and we have our fault at 178 feet. Here's some examples, some real examples. Up here in the top right-hand side, you can see we have a fault out almost at 8,000 feet. And if you look reading from left to right, you can see the red and the blue trace track each other. They even track each other right through this, some type of splice or impedance change. Blue's tracking a little bit, but out here at about 8,000 feet, we have this very characteristic V shape. That's what we're looking for. This would be representative of a typical pinhole fault in the insulation. Again, the red line is tracking the blue line, and at some point there's that sharp downward blip. Now down below we have kind of a special case. This is really not that unusual, where if we look at the trace, the fault distance and the open end of the cable, the bump up and the bump down are at exactly the same location. And this occurs when the center conductor of the faulted cable has been severed in half. And that can happen sometimes from the, during the outage, there's fault current through that center conductor, and it can blow the conductor in half. It could also happen where someone has literally dug in and chopped this cable in half. So the characteristics, again, they're just like before, reading left to right. The red line follows or stays right on top of the blue line. When it reaches the fault area, you get that sharp downward V shape. Okay. Yes.
Before we move on, can we have a couple of questions from the audience?
Sure, go ahead.
Okay, so someone asked, does the ARM method cause more damage to the cable being tested?
So there's a study out there that shows high voltage impulses can be damaging to a cable. Now, if you actually read that study, they were talking about lightning bolt pulses from lightning strikes. And they also took one of the largest thumpers made at a very high voltage setting and showed that there is a possibility of impulse damage to a cable that's already heavily aged. So I would contend that your typical arc reflection shot, we haven't gone through the whole process, but typically you're doing these arc reflection shots pretty close to phase to ground operating voltage. It is an impulse, but I would contend that from a practical point of view, the arc reflection is not going to cause any additional damage to the cable. Now later in the fault locating process, excuse me, you will turn your thumper on, and the whole point of the arc reflection is to quickly prelocate your fault with a single shot, and then that will minimize the number of thump impulses you have to put into the cable. To summarize that, I guess, is today's fault locating process, if done properly, is going to not cause any additional damage or very additional damage.
Okay. And another question. So can a TDR test tell us how much of a concentric neutral remains good on a cable? So let's say, can you know if it's 50% good or not? And what's the benefit of using a TDR over resistance testing, such as an all-make check for the testing the integrity of concentric neutrals?
You know, this is a pretty broad topic, but in general, the TDR cannot tell you what level of concentric neutral damage you have. You can get an indication from how bumpy the trace is that there's some concentric damage and microimpedance changes up and down the cable. And again, there's been one paper that I'm aware of where they took a radar and they were able to, you know, show that yes, we can see damage. But from a practical point of view, you can't really do it. And what I mean by that is you would have to have a very high resolution TDR, and you would have to test a bunch of cables and get a good feel for what those signatures look like. Then you would have to dig all those cables up and say, all right, that signature matched this level of degradation of the neutral. So theoretically, you could do it, but from a practical point of view, you can't. To my knowledge, the only way to actually get a true indication of how corroded the neutral is, there's a method where you can string a reference wire above ground and using that reference wire, use a bridge technique. So from a practical point of view, a TDR might give you an indication that you've got some damaged neutral, but you can't really put a number on it.
Okay, thank you, Marshall. I guess we'll move on and keep your questions coming. We'll answer them as we have time or towards the end of the presentation. Okay,
so moving on then. You know, part of the fault locating process, you know, an optional step but highly recommended is to trace the cable path. And this is where you transmit a signal onto the cable with some type of transmitter shown here. You can see they're connected up to the cable, and that's going to inject a signal onto the cable. And then we're going to use a receiver and sweep back and forth and trace that cable path. Now, the reason I'm popping this slide into the TDR presentation has more to do with the next slide. Why trace the cable path? You know, sometimes the cables, they have extra loops or bends or an unexpected route. And when we're doing arc reflection, the arc reflection gives us a distance to the fault, but the cable path might not be a straight shot. And, you know, we try to show that here with this diagram, is the arc reflection said the fault is 1,200 feet away. So this red star out here would be the physical location on the ground if we just measured in a straight path from the left-hand side over here, our hookup point. But if we could see down into the dirt, we would see that the cable path really doesn't travel in a straight line. It might even be on the other side of the street. So we're over here looking for a fault when in actuality it could be quite a big distance away from us. So tracing the cable path is something that is not necessary. You don't have to do it every time, but it's recommended to help with this next slide, TDR accuracy. If we go through the accuracy of a TDR, we've got several factors to consider. The first factor is correct propagation velocity, where the propagation velocity can use an average number. It can use a chart or a guideline or a predetermined number where we've taken a known length of cable and figured out what the propagation velocity is. Known cable path, and that's you know, as in the prior slide, that's why you might want to pre-trace or pre-locate the cable so that you're measuring out the same distance above ground that you acquired with your TDR. And then cursor placement. This is probably the least important. The cursor is placed on the left-hand side of the trace variation, right where the trace bumps up or down. Or even better, you place it right where two trace splits apart. You know, if we look at it, propagation velocity, generally this is your biggest factor in accuracy. Known cable path, if you've traced the cable, this isn't going to, there's not going to be much difference between you and the walking above ground and what you measured with the TDR. However, if you haven't traced the cable path, this could be a big factor. And then cursor placement is a fairly minor factor. Again, you know, in cursor placement, the best would be if you had two traces that split apart, you can put the trace right exactly where, or the marker right where they split for a very accurate measurement. Okay, I need to pause here for a minute, and I just realized I skipped a very important part. Let me jump back in here. So the 4 common adjustments, I want to show these to you. So let me pop out of my PowerPoint presentation here, and I apologize, I got a little out of sequence here. I have a simulation, some software that we use for training, different products that we sell. But what I can do with this simulation box is I can actually go in here and show you propagation velocity, show you how to adjust the display range, the gains, and the cursors. These are the 4 common adjustments if you're manually running a TDR. So what I'm doing here is I'm starting the locate process on this particular piece of equipment. And so this simulation, in this case, the TDR is actually automatically going to adjust the gain and find the end of the cable. And you can see the software did it for me. It said, oh, your cable end is most likely at 1,000 feet. And we can confirm this. Now, using this software, I can also show you how you would manually do some of these adjustments. And let's start with propagation velocity. So if we look at this particular trace, the end of the cable is out at 1,000 feet, and that was calculated using a propagation velocity of 262 feet per microsecond. And there's 2 ways we can adjust that. We have a manual adjustment where I can simply increase or decrease the velocity. Now, if you watch, as I decrease the velocity, the distance is recalculated. So now, if we told this radar that the velocity was 254 feet per microsecond, our calculated distance would be 30 feet shorter, 970 feet. And of course, if we make it bigger, then the distance gets bigger. So that's one way you can manually adjust propagation velocity. Probably the more common way to adjust it for the casual operator of this equipment would be to use some kind of chart or list. Excuse me. So here we have a list of different cable types with different propagation velocities. Now, if we go down in this list and we find some type of cable that's really, you know, not even close in impedance to a typical medium voltage power cable, let's take a telephone wire, which uses 485 feet per microsecond, and click on it, it's changed our velocity setting, and look what it did to our calculated distance. It's now it's 1,847 feet. Now the length of this cable from left to right, the physical length of the cable never changed. But if you do wild swings in propagation velocity, you can really impact the length. So this is an important setting. Now, if we go back into the chart, a typical factory setting might be 252, 255, somewhere in this range. And generally, if we look at that chart, Power cable tends to be in the same ballpark. So if whatever your radar is set at on short length cables, you're going to be relatively close without changing your propagation velocity. But if you want to be accurate, you can go in and manually adjust it. You can pick off a chart. The most accurate way to set propagation velocity is for the exact type cable that you're measuring. Someone's gone out and taken a known length of that cable and has made their radar match that known length, and that tells you exactly what the propagation velocity is. Okay, moving on. Visible range. If you look at this screen, we have this distance open end at 979 feet, but right underneath of it, we also have this grayed out distance of 1,125 feet on the right-hand side of the screen, and over here on the left, we have 0. These distances are just from the left side of the screen to the right side of the screen. They're simply showing how wide our view angle is. If we go in and change it, I can increase it or decrease it. Here I'm decreasing it, and notice I can't even see the end of the cable now. When you set display range, you want to see the end of the cable. And of course, if I go out, like this particular radar could go out to 80,000 feet, and it's scrunched our short little 1,000-foot cable up here clear on the left-hand side of the screen. But generally, if you manually set the range, you would look past the end of the cable, make sure there's nothing out here, and then position it over here on the right-hand side of the screen. And whenever you made the cable fit onto the screen, that in essence has set your display range. Okay, the other adjustment would be gain. If we click on gain, now if we look at the amplitude of the end and also the amplitude of these large impedance changes, if we increase the gain, the amplitudes get bigger, and we can decrease the amplitude. There's some personal preference in this. There's some reasons to adjust the gain up or down when you're fault locating, but basically using the end marker, somewhere about 50% from this line up to the top is generally where it would be set. And then last we have cursors or distance markers. You can see we have this blue marker here, this vertical line that says the end of the cable is 979 feet. Let's say I wanted to measure to this impedance change right here. I could grab a marker and I can just, slide it back and forth, and I have this course adjustment. And then if I click again, right on the left-hand side of this impedance change, that's the distance to that particular impedance change. In this case, it's 605 feet. And what I'm trying to show you here is every TDR out there has some type of distance marker or cursor. And, you slide them back and forth to wherever they need to be. Okay, so let's jump back into our presentation.
Just one really quick question.
Sure.
Where can we find the cable velocities if it's not programmed in the software?
Well, we could certainly send out the list that we have. Every manufacturer is probably going to have lists. Sometimes these are printed right on the TDR, but if you don't have one, you would just, you can request one. I would say these propagation lists are very they're guidelines at best. They're not necessarily that accurate, but if that's all you've got, they're going to get you closer than an average setting.
Okay.
Any other questions on that?
Not right now.
Okay, let me jump back to, and I apologize for getting out of sequence here. Let me go back to where we had stopped before. We had finished with, or we were discussing TDR accuracy, and So to just kind of re-summarize on accuracy, you do want to have the right propagation velocity. And again, there's three ways you can get it. You can use an average number, a setting, if you will, that you never change. And that works good for shorter power cables. You can use that charter guideline. And again, we could get you the one that we use. Just be aware that, these guidelines they're not necessarily that accurate for your specific type of cable. Different age cable, different manufacturers, all those things add up. The most accurate way would be to take a known length of your cable and using a TDR, match your TDR measurement to that known length, and that would give you the exact propagation for that specific cable. Then when you're out there working with it in the field, you need to know your cable path. You might need to prelocate or pre-trace the cable. And then when you actually adjust your radar, when you're sliding those markers back and forth, basically you place the marker on the point of interest on the left-hand side, right where the trace varies up or down, or better, place it right where two traces split apart. Okay, there's another fairly common application for the TDR out in the fault locating world. Excuse me, and that's to use it to sectionalize with. And if you look at our presentation here, down at the bottom, we have a circuit shown. This is 3 transformers with sections of cables in between. So this would be, representing a section of a loop feed. Now, sometime in the middle of the night, one of these cables failed. It faulted, and everybody on this loop lost lights, lost power. So a troubleman comes out there, and his job is to figure out where this fault is so he can isolate it and restore power by looping around, feeding power from either direction around an isolated faulted cable. There's different ways to do it, but when you're using a TDR, what you would use is the arc reflection method, where you use your thumper and you charge it up and you do one of these single releases of energy. So you do your arc reflection shot, and the high voltage pulse travels down, creates the arc, and we see the fault up above just like before. Now, in addition to seeing the far end, we also see these wiggles. These are your transformer impedances, and we can see where the fault is in relationship to the transformers. But we can go a little bit further than this. No, we can see where the fault is, and here's a example of a real world case where here's the end of the cable. There's some transformers in here, and the impedance changes are not necessarily that uniform. We can clearly see that red V shape where the fault is, but the other thing that we can do is we can also tag or put distances on the transformers themselves. So if you look here, we have a T1, a transformer 1 at 175 feet from the point of hookup. Then there's a second transformer, and then there's a third transformer. And we can see that the fault lies between T2 and T3. So that gives the operator a good set of information on where to go down his circuit. He would go down to this transformer 2 and 3, isolate this cable, verify that it's faulted, and if it was, if he verified that he found a bad spot, then he can quickly loop around and restore power. And then it's probably the middle of the night and rain, and he's going home. Later, someone will come back on this isolated cable and do a precise fault locate and either repair that cable if it's direct buried, or perhaps pull and replace it if it's in a conduit. Okay, so that kind of wraps up the presentation. Are there any other questions to answer at this point?
Yeah, we actually have a whole bunch of questions. Let me start from, I guess, the most basic one. So, are there specific TDRs for specific cables? For example, do you use different TDR for oil field cables versus XPLE, etc.?
Well, when we talk about high voltage power cables, you could pretty much use. Well, let me back up a minute. I mean, this is actually a good page to answer that. Is here you can see a whole bunch of different TDRs. And over here on the left-hand side, we have these little handheld TDRs. And all of these TDRs would look down the same cable, but here on the right-hand side, these TDRs are specifically designed to work in conjunction with that high voltage pulse from a thumper. In fact, here's a picture of one, a small thumper with an integrated TDR. If you want to do arc reflection method, you have to have a TDR that's designed to time itself with a thumper. If you simply want to do low voltage measurements, you could accomplish that with any of these TDRs. So in general, to just take low voltage measurements, you don't need a specialized TDR. But for power cable, in almost all cases, you're going to be using one where you can combine it with some high voltage steps.
Okay. And what is the approximate length of a cable that the TDR can send a pulse down?
Typical TDR lengths would be like 25,000 feet maximum, 80,000 feet maximum. We have some specialty TDRs that can see, farther than that. It's not very common to have a cable that's too long for your TDR to see to the end of it.
Mm-hmm. And can the TDR detect electrical or water trees? Does the pulse look different for these?
No. In order for the TDR to reflect off of an impedance change, and you could think of a water treat cable, as having impedance changes in it. The impedance change has to be pretty significant. So you can have a electrical tree, which that's what a fault is, if you will. It's where the insulation's completely broke down. The TDR can't see that by itself. You have to create that arc. We do have test and diagnostics methods that can tell us how severely damaged the insulation is. That would be, probably the 10 delta test. We have partial discharge testing, which combines a creation of partial discharge with a TDR technique. So there's TDR techniques are used in diagnostics of cable, but just to hook a low voltage TDR up, it's not capable of seeing water train or anything like that on its own.
Okay. Some other questions. Would the TDR work on a neutral that's completely corroded?
No. And that was, let me just go back really quick so this example, in this case, right here at this location, the neutral is corroded away. That's what we're trying to show here. And this is really, over here on the right-hand side is the literal far end of the cable. But right here, the neutral's corroded away. We hook the TDR up to it. We send the pulse down, and 100% of the signal reflects back right from where the neutral's corroded. Now, when I say corroded neutral, I'm qualifying that. Completely corroded away. There's no longer any electrical continuity through that corroded neutral. Many times the neutral, like on an unjacketed cable, is damaged, and you can see the far end. And that actually, and that's one of the reasons you would do this test, where you go to the far end of the cable, and you apply a ground, and you see the trace flip up and down as you apply the ground on and off. That verifies that the center conductor and the neutral concentric have electrical continuity. Your neutral could be corroded, it could be damaged, but it's good enough for the TDR to see through it.
Mm-hmm. And can a TDR distinguish between a fault in a cable and just a poorly constructed splice?
No. If I'm understanding the question right, again, if we back up in the presentation, to this slide, and this has a splice in it, and if we, we're going to get some kind of an impedance change like this, and if if this splice was poorly constructed, the chances of seeing it with the TDR, a difference between a good splice and a poor splice, is pretty slim. If you made the impedance in this splice bad enough, big enough, you might be able to, like if you did comparisons between, say, 15 splices that were all constructed at the same time, and one was just radically bad, you might see the difference. But really the right way to do that is with the partial discharge test. The partial discharge test will nail that bad splice just every time, just about, whereas the TDR, from a practical point of view, it's not done.
Okay. I think there are some general questions about connections. So are we required to ground the other end of the cable before we dump it?
Oh, no. When you apply high voltage, if we use this cable right here, actually let me bump down to a slide where we're showing a thumper. Okay, let me jump into this one here. So here we have, this is a very simplistic diagram. We're not showing all the grounds, but this cable that's represented here, the neutral concentric of this cable would be tied to system ground at both ends, and we're not going to change that when we hook up our equipment. Now, before we hook up our equipment, the operator is going to test and ground that cable dead per that specific utility safety procedures. At that point, we're going to connect our thumper to the center conductor and the neutral concentric at one end. And the far end of the cable, the center conductor of the far end, is just going to be stood off or parked. And so I'm not sure if I'm answering the questions, but we're not going to interrupt with any of the system grounds. We leave it exactly the way it is. We follow our safety procedures. We hook our thumper up, which, by the way, is hooking the radar up at the same time. We're using the same cable for the radar and the thumper, and the far end is stood off. If we grounded the far end, the center conductor of the far end, the energy from the thumper would have a very easy path to flow to ground. We want the energy from the thumper to flow through this fault. So again, we charge the thumper up, we do a single shot, releases the energy, we get our fault distance. Now later on, we would turn the thumper into the cycle mode, where it would cycle in the direct thump mode and try to make acoustic energy there. This presentation is focusing mostly on the TDR, and we're talking about the arc reflection method, but there's other steps to actually pinpoint that fault, to put paint on the ground exactly where the fault is.
Okay. There's a question about what's the maximum thump that you can or should send through a cable?
Let me just pop open another this is another presentation. Whoops, that's not the... Yeah, all right. So as part of the fault locating process, the first thing you would do is you would verify that that is a faulted cable you're working on, and we do that with a breakdown test. So here we have our thumper connected to a faulted medium voltage cable, and we use a function in the thumper called breakdown. It's a DC high pot. We raise the voltage up on this. We're charging that cable up with high voltage, and we reach breakdown. And we're going to, if we run this again, if you watch the needle here, at about right around 12 kV, we achieved breakdown. So that, in essence, tells us how high to run the thumper. You do your breakdown test, and it says, oh, you have breakdown at 3.5 kV, then even though that cable may, it's 25 kV class cable, maybe it normally runs at 19.9 phase to ground. We only need 4 or 5 kV to break it down. We would probably run our thumper at, 6, 7, 8 kV, just a couple kV above breakdown.
Okay. I think on one of the slides you were showing transformers on the network. So is it safe to thumb through transformers?
Okay, so when we talk about sectionalizing, where we're going through transformers, again, this is not really a TDR question, but the output of the thumper itself, when we do this coming out of the pump, it's what we call an arc reflection shot. The discharge is through a choke filter. And what it does is it takes this high energy pulse and it kind of spreads it out over time. And the idea is to create an arc to reflect off of. That's really not the same as thumping to make noise. If we were actually wanting to dig this fault up and put a splice in here, we would not leave the thumper connected here. We would not turn it on in the cycle mode and begin to thump repetitively from here. We would isolate this cable and we would connect the thumper up at either this transformer location or this on the isolated cable, and then we would use the cycle mode. So you don't use the cycle mode through transformers, but the high voltage pulse coming out of the thumper, it's a high frequency pulse, and it travels quite finely right through the transformers. It's not going to cause any. We don't recommend that you use the thumper in the cycle mode going through transformers. There's no reason to do that either. If you're actually trying to put paint on the ground to say this is exactly where I want to dig up and put a splice in here, you can always do it on the isolated cable.
Okay, I think we're running out of time, so maybe just one last question. So when specifically do we apply the arc reflection method? Is it just for high voltage cables, and can it be used on concentric secondary cables?
That's a good question. For secondary cable, if it has a shield, if it has a concentric, which that's not very common, but there are some secondary cables like that, you definitely can use the thumper. We offer thumpers that are actually restricted in their voltage range that they might use like in a mine environment or something like that. But if you're talking about typical triplex secondary cables, you would not use the thumper. You would use a voltage gradient method. So there's, depending on what type of cable construction you're working with, that dictates to you what's the best troubleshooting techniques. And arc reflection on a medium voltage shielded cable is usually the right technique. But for other type cables, there's other techniques. And then let me just then wrap up with, again, we have these different type of radars. We're back to this last slide. These fault locating radars, the link up at the top of the page will take you to them. And for the handheld TDRs, the link down here on the lower left-hand side will take you to them. And if we're out of questions, I think that's the end.
Yeah, well, we aren't out of questions, but we're out of time. But if we didn't get to, if we didn't get to your question, we'll follow up with you individually via email after the presentation. You will get a copy of this presentation in the next couple of days, and the recording of the session will also be available on our website about 2 weeks after the presentation. So when we close, you'll be directed to a survey that you can fill out. Please do fill out our survey because we really appreciate your feedback so that we could continue to improve future webinar sessions. And Thank you all for attending. Have a good holiday season. See you guys in 2016.
Thank you. Bye-bye.